Today we're going to have an in-depth conversation about FinOps for GenAI workloads. So when you think about GenAI workloads, the cost structure is fundamentally different from traditional cloud computing. We need to understand there are three primary cost domains, and each of these requires different cost optimization strategies. The first domain is the training and fine-tuning costs. This is characterized by the high upfront GPU compute investment. When you're training or fine-tuning a model, you're paying for expensive GPU clusters, typically A100 or H100 instances. You also have data preparation and experimentation cycles where you're spending engineering time cleaning, labeling, and formatting training datasets. And then there's infrastructure setup and modeling versioning. This is primarily a capital expense that happens upfront. The second domain is the storage and retrieval cost. This is particularly relevant for RAG systems. You have vector database that scales with your document count. The more documents you need to search through, the more storage you will need. And you have embedding generation and query processing costs. Every time a user, let's say they ask a question, you're generating embeddings and doing similarity searches. And you have document storage and update management as well, which involves managing the lifecycle of your knowledge base as it evolves over time. The third domain is the inference cost. This is your ongoing operation expense. Token consumption and API calls are your primary cost driver here. Every query you process costs money in tokens. You need compute resources for model serving, whether that's self-hosted GPU instances or API-based serving. And you have caching and optimization layers that can reduce these costs, but they also add architectural complexity. Now, for context throughout this presentation, the cost estimates I'll be sharing assume that 7 billion to 13 billion parameter models are being considered here. If you're working with larger models, let's say 70 billion parameters and above, you should expect costs to be 5 to 10 times higher across all these dimensions. The relative economics still apply, but the absolute numbers scale up pretty significantly. Understanding these three cost domains is critical because the optimization strategies for each one are pretty different. Now let's break down the economics of fine-tuning. This is important because fine-tuning has a very specific cost profile that differs dramatically from other approaches that we'll be discussing. First, let's talk about the upfront costs. These are one-time expenses. So the training compute for small to medium models, which would be 7 billion to 13 billion parameters using efficient methods, typically runs from $5,000 to $50,000. This wide range depends on how many training iterations you run, your hyperparameter tuning process, and whether you're using the full dataset or a subset for experimentation. If you're doing full parameter fine-tuning of large models, you could easily exceed $100,000. The good news is that parameter-efficient methods like LoRA or QLoRA can reduce these training costs by 75% to 95% versus full fine-tuning, while maintaining the clock quality for many of the use cases as well. This is because they dramatically lower the GPU and memory requirements by only training a small subset of parameters. You also have data preparation time, which is typically 2 to 4 weeks of engineering time. This is not just about collecting data, it's also about cleaning it, ensuring quality, formatting it correctly, and often manually reviewing and correcting examples. And then there's the infrastructure setup, which involves building ML pipelines, experiment tracking systems, and model registries. This is usually a one-time investment that you amortize across multiple fine-tuning projects. Now for monthly operating costs, which are your ongoing expenses. So self-hosted GPU serving typically runs from $500 to $3,000 per GPU per month, depending on whether you're using A10G instances on the lower end or let's say A100 instances on the higher end. API-based serving has variable per token costs, but it's typically lower than the base model APIs because your fine-tuned model can be smaller and more efficient at this specific task. You also have model storage and versioning at around $50 to $200 per month. This scales with how many model versions you keep and how frequently you retrain. And you also have monitoring and observability tools to keep track of quality drift, performance metrics, and when you need to actually start retraining. The key insight here is that fine-tuning is a high upfront investment with relatively low ongoing per query costs. The cost structure means that it only makes economic sense under certain conditions, which we'll explore next. So when should you actually consider fine-tuning? This is where understanding the break-even economics becomes super important. Let me give you a concrete example. So let's say you spend $25,000 on training costs and your fine-tuned model saves you $0.002 per query compared to using a base model. maybe because your model is smaller and now more efficient, or because it requires shorter prompts. Your break-even point is at 12.5 million total queries. Now, this would happen in different ways. Let's say 500 queries per month for 25 months, or 2 million queries per month for just over 6 months. The key word here is total. We're talking about cumulative query volume over the lifetime of the model, not just the monthly rate. As your cumulative query volume increases, the economics of fine tuning improves because you are amortizing the upfront cost over more and more queries. Now let's talk about the favorable conditions where fine tuning makes sense. First, you need sufficient query volume to amortize the upfront costs. I typically look for a 6 to 24 month payback period depending on your organization's financial constraints. Number two, you should have the domain specific terminology or knowledge that's not well represented in base models. This could be medical terminology, legal language, or internal company jargon that base models handle very poorly. Third, you have a consistent task format, things like classification, entity interaction, or structural output generation where the input output patterns are predictable. And fourth, the quality improvement from fine tuning justifies the investment. If prompt engineering, let's say, gets you 90% of the way there, then maybe you do not need fine tuning. But there are challenging conditions where fine tuning actually does not make sense. First, rapidly changing requirements requires rapidly, frequently retraining. If you're retraining every month, you're constantly paying that $25,000 cost and you're never really getting the long term benefits. Second, insufficient total query volume to actually recover the cost. If you're only doing 50,000 queries per month and do not expect growth, the math just doesn't work here. Third, limited training data. You typically need 1,000 to 10,000 plus quality examples depending on the task complexity. For simple classification, 500 to 2,000 examples might be okay. And for complex reasoning tasks, you might actually need 10,000 to 5,000 examples. For domain specific language, you could need 20,000 plus examples, which would be ideal for this scenario. And number four, tasks where prompt engineering achieves acceptable quality. So, for example, why would you invest in fine tuning if you can get 90% results from prompt engineering techniques and optimizations? So, the strategic question you should ask is that will we execute enough queries over the next 12 to 24 months to justify this upfront investment? Let's contrast that with the rack systems, which will have a completely different cost profile in the upcoming slide. Now, let's look at rack systems, which have a fundamentally different economic model. They have zero upfront training costs, but they do have ongoing operational expenses. For setup costs, which are one time expenses, you have document ingestion and embedding generation. This typically runs $100 to $1,000 depending on your document count and the embedding model you're using. If you're using a service like OpenAI's ADA002, you're paying per token embedded. Infrastructure development takes about 1 to 2 weeks of engineering time to build your document processing pipeline, chunking strategy, and retrieval system. And you also have a vector database initialization, which involves getting your first batch of documents embedded and indexed. Now, for monthly operating costs, which are your operating ongoing expenses, for vector databases that will typically cost $500 to $5,000 per month depending on the scale. Now, it depends on how many documents you'll be storing, your query volume, and whether you're using managed services or you're self-hosting. And here's also an important cost factor. Managed services like Pinecone or Azure AI Search, they roughly cost 3 to 5 times more than your self-hosted options like running a vector database on your own infrastructure. But they do save you a lot of operational overhead and DevOps costs. Query embeddings cost $50 to $500 per month based on your query volume. Every user query needs to be embedded before you can do a similarity search. LLM inference with retrieval context is typically your largest cost here, which is at roughly $1,000 to $10,000 per month because RAG systems they send larger context to the LLM than you would with other approaches. And then you have the document updates with incremental embedding costs as your knowledge base evolves and grows. The scaling characteristics of RAG are quite predictable. Costs increase linearly with document count and query volume, which makes cost forecasting pretty straightforward. You do not have training investment, but you do have higher per query costs compared to fine tuning at scale because of the retrieval overhead. Every single query triggers embedding generation, vector search, and LLM inference with an expanded context window. The key trade off here is that time to market versus long term operational costs. RAG systems can be deployed much faster than fine tuned models, but If you're only running millions of queries per month, those per query costs, they do actually add up. So when does RAG system actually make economic sense? So the scenarios when it actually makes sense to have RAG system, it depends on your workload characteristics. For favorable conditions, the first is a frequently changing knowledge base where retraining would be very expensive. If your documents are updated daily or weekly, retraining a fine-tuned model every time would be very expensive. RAG just requires re-embedding the changed documents, which is much more cheaper. Second is the source attribution and explainability requirements. RAG systems naturally provide you citations because you're retrieving specific documents and you can show the users exactly where the information came from. This is critical in domains like healthcare, legal, and compliance, where you need to justify every answer. Third is a moderate query volume, let's say in the range of 10,000 to 1 million queries per month. Below this, even simpler approaches work fine. Above this, the per query costs start to accumulate pretty significantly. Fourth is the documents with clear structure and well-defined topics. RAG works best when your retrieval can cleanly separate relevant information for it from the irrelevant information. And number five reason is for using RAG system is existing document management infrastructure. Let's say if you already have a document system, adding RAG on top of it can be pretty low cost investment. But there are certain challenging conditions where RAG systems also struggle. First is very high volume query volume exceeding let's say 5 million queries per month. At this scale, retrieval costs accumulate to the point where alternative architectures become much more cost effective. Number two is where simple FAQ scenarios where caching can actually eliminate most retrieval needs. If users are asking the same 100 questions over and over, and you're better off just caching the responses than doing retrieval every time. Like for example, you build a chatbot for your support system or your FAQ on your website, then roughly a lot of questions that users ask, they're typically very similar. So you can actually get the responses from the caching system rather than actually retrieving it from the vector database. And number third is the reason is that extremely large collections exceeding let's say 50 million documents where vector database costs can exceed at that point $10,000 to $50,000 per month. At that scale, you need to think carefully about whether you need all these documents searchable or if you can just tier your storage, let's say in tier 1, tier 2, and tier 3, and then architect it that way. And number four challenge is the real-time latency requirements, where retrieval can add unacceptable delays. Let's say if you need to have a sub 100 millisecond responses, then the overhead of the embedding generation and the vector search can become a concern. The key advantage of RAG is the zero upfront training cost and faster time to production. You can have a working system in days rather than weeks. The trade-off is that it's a higher per query cost due to retrieval overhead. Every query does embedding generation, vector search, and larger context window inference. Now, regardless of whether you choose fine-tuning or RAG, there are inference optimization techniques that apply universally to reduce the costs. So now let's explore them in the next slides. Now let's talk about inference optimization and how it's super important for cost optimization when building GenAI apps. So these are not alternatives to fine-tuning or RAG. These are techniques you apply to whichever architecture you end up choosing. Many teams make the mistake of treating optimization as an either-or decision with architecture, but they are actually complementary. First, let's talk about token optimization. Prompt compression is about removing verbosity and using concise instructions. Instead of saying, please analyze the following document and provide a comprehensive summary, you can actually just say, summarize this document. You're actually conveying the same intent with fewer tokens. Context pruning means including only the relevant retrieved documents and not actually the entire corpus. If you retrieve 20 documents but only 5 are truly relevant, then you just include those 5. Response level limits and structure outputs help control output token consumption. Instead of letting the model generate a verbose response, a very long one, you might just constrain it to let's say 200 tokens or ask for a JSON output. Stores responses for identical queries and typically achieve a 15 to 30% hit rate in FAQ systems where users ask the same question repeatedly. Semantic cache uses embedding similarity to retrieve responses for semantically similar queries, expanding your hit rate to up to 40 to 60%. For example, how do I reset my password and what's the process for password recovery would ideally hit the same cache entry. Now, production systems typically achieve 20 to 50% overall cost reduction through caching, depending on the query pattern repetitiveness. Highly repetitive domains like customer support FAQs can reach 50 to 70% hit rates because users really are asking the same question over and over. But if you're building a research tool where every query is unique, your cache hit might only be to 5 to 10%. So the savings would be much, much lower. The critical understanding here is that these techniques are universal. Whether you're using a base model, a fine tuned model, or a rack system, you should be applying token optimization and caching. They are complementary practices and not alternative to your architectural choices. Now let's look at two more optimization techniques that can significantly reduce costs: model routing and batch processing. So now let's get into a bit more here with the model routing to start off with. The insight here is that not all queries require the same level of model capability. Small models handle simple classification and FAQ matching at a baseline cost. Let's call this 1x. These might be billion parameter models or even smaller. Medium models handle general Q&A and summarization at 5 to 10 times the baseline cost. These are your 13 billion to 30 billion parameter models. Large models handle complex reasoning and technical content at 50 to 100 times the baseline cost. These are your 70 billion plus parameter models or the frontier models like GPT-5 thinking. Now, let me give you a concrete example of the impact. An enterprise support system that we designed in the past routed 60% of these small queries to smaller models for simple FAQs, 30% to medium models for troubleshooting questions, and only 10% to the large models for complex technical questions. This achieved a 45% overall cost reduction for us compared to if we were using large models for everything. The key here is having a good complexity classifier at the front, usually a small, fast model that determines which tier to route to. Now let's talk about batch processing. This is pretty critical as well. The batch processing only applies to self-hosted models, not the API-based serving. Batching improves GPU utilization for self-hosted models because you're processing multiple queries in parallel. A batch size of 8 to 16 can reduce cost per query by up to 40 to 60% because you're amortizing the model loading overhead across multiple requests. However, it does add 50 to 200 milliseconds latency while you wait to accumulate a batch, making it unsuitable for real-time interactive applications. And here's what many teams don't quietly get correctly, which is that this does not apply to API-based serving from providers like OpenAI or Anthropic. You're billed per token regardless of whether you send requests one at a time or in parallel. So the batching happens on their side and you don't see the cost benefits. The model selection impact here is pretty significant. You should route queries to appropriate size models based on complexity and avoid over provisioning for simple tasks. If someone is asking what's your return policy, you don't need an advanced model like GPT-5 thinking to answer that. Now, these optimization techniques can be applied to any of the three fundamental architectures. Let's compare those architectures head to head. Now, as part of doing the comparison, let's start with this is where the rubber meets actually the road in terms of making the architecture decisions. Architecture 1 is a base model plus optimizations. This means you using general purpose models like GPT-5 or Claude with caching and token optimization applied. You have no custom training or retrieval infrastructure to build or maintain. This offers the fastest time to market and you can be in production in days. You have moderate per query cost because you're paying full API pricing, but you're optimizing token consumption. This is often the right choice for experimentation, rapid prototyping, or applications where query volume does not justify the investment in alternatives. Architecture 2 is rack system plus optimizations. So this is where base or smaller models with vector database retrieval plus caching or token optimization will be there. You're essentially adding retrieval infrastructure, which increases complexity but allows you to work with your own knowledge base. There is zero training cost, which is a major advantage here. So you're not paying $25,000 upfront, but you have higher per query cost due to retrieval overhead, which is embedding generation, vector search, and larger context windows. This works well when your knowledge base changes frequently or when you need to have the explainability and citations as part of the system. Now, architecture 3 is fine-tuned model plus optimizations. This custom trained model with self-hosted API serving plus caching, batching, and all optimization techniques. There's a high upfront cost is a barrier to entry, which is roughly from $5,000 to $50,000 training investment. But you do get the lower per query cost at scale because your model is optimized for a specific task, and that's why it can be smaller and more efficient. This makes sense when you have high cumulative query volume and stable requirements. The key insight here is that all three architectures benefit from optimization techniques: caching, token optimization, model routing. These apply regardless of which foundation architecture you choose. Your choice of architecture should be driven by query volume, knowledge update frequency, and quality requirements, which will quantify the cost of comparisons. So now let's get into real numbers. This is where we can start plugging into our query volumes and see which architectures make more sense for our specific use case. At 500,000 queries per month, here's what you should expect. Base model plus optimization runs $33,000 to $5,000 per month. You're paying for API calls with some cost reduction from caching and token optimization. Rack system plus optimization runs roughly $3,500 to $6,000 per month. You have the additional costs of vector database hosting, embedding generation for queries, and larger context windows. Fine-tuning model plus optimization runs roughly around $2,500 to $4,000 per month, but this does exclude the training cost amortization. So if you just train the model, you need to add the portion of that $25,000 to your monthly cost until it's fully amortized. Now, at 5 million queries per month, this picture changes dramatically. The base model plus optimizations jump to $25,000 to $40,000 per month because these per token costs really accumulate at the scale. A rack system plus optimization runs $35,000 to $60,000 per month. The retrieval overhead compounds as volume increases. The fine-tuned model plus optimization runs only $8,000 to $18,000 per month, with training costs now amortized. You can see how fine-tuning per query cost advantage becomes significant at this scale. So now some scaling observations here. Base model costs accumulate linearly with volume. You're essentially paying a fixed rate per query. RAG retrieval overhead scales proportionally as well because every query does embedding, search, and expanded context inference. Fine-tuning shows a dramatic per query cost advantage at scale because you have already paid the training cost and your ongoing costs are just inference. But monthly costs don't tell the full story. To make the informed architectural decisions, you need to look at the total cost ownership of over next 12 to 24 months. So let's do that analysis next. So this is where the economics becomes much more clear because we're including both the upfront and the ongoing costs. So for 12-month TCO at 500k queries per month, which is 6 million total queries, here what you should expect. The base model plus optimizations cost 36k to 60k dollars. This is just 12 times your monthly cost since there is no upfront investment. The rack system plus optimization costs 42k to 72k. Again, 12 times monthly cost with minimal setup cost. Fine-tuned model plus optimization costs 55k to 73k, which includes the $25,000 training cost amortized over the year. At this scale, fine-tuning is actually more expensive than the alternatives because you haven't done enough queries to recoup the upfront investment. But now let's look at the 12-month TCO at 2 million queries per month, which is 24 million total queries. So base model plus optimization cost 120k to $216,000. The rack system plus optimization cost 168k to 288k. The fine-tuned model plus optimization costs approximately 95k to 165k. At this volume, the $25,000 training cost has been fully amortized and represents only the 15 to 25% of your total cost. Fine-tuning now shows a clear cost advantage. Here are the economic inflection points you should understand. Fine-tuning achieves cost parity with base models around 12 to 15 million cumulative queries, which aligns with our break-even calculation. At 24 million queries, fine-tuning delivers approximately 25% to 35% lower TCO compared to base models, and even more significant savings, around 40 to 50% compared to rack systems, due to rack systems retrieval overhead. These advantages becomes more pronounced as you scale beyond 50 million queries, where the training cost becomes almost negligible as a percentage of the TCO. Break-even timing depends on your monthly query rate and training costs. So if you're doing 2 million queries per month, you hit the break-even point around roughly 6 to 7 months. If you're doing 500 per month, it takes closer to 24 months to break even. The strategic insight here is to project your cumulative query volume over 12 to 24 months, not just look at the current monthly rates. Many teams take decisions based on the current load and don't account for the growth in the upcoming years. Now, knowing these economics is one thing, but how do you actually make the decision? So let's work on a decision framework now. So now let's cover a practical decision framework you can use to choose the architecture. So this is not about rigid rules, it's just about understanding what factors push you towards what option specifically for your business use case. So first is query value volume analysis. For low cumulative volume, meaning less than 5 million total queries, you should choose base model plus optimization. The upfront investment in alternatives just doesn't make sense in this case. For medium quality cumulative volume, which is roughly from 5 million to 20 million total queries, you should choose RAG or base model based on knowledge dynamics, which we'll discuss in a moment. For high cumulative volume exceeding 20 million total queries, finding economics become much more favorable because you have sufficient volume to amortize the upfront training costs. Now, second is knowledge update frequency. For static knowledge that rarely changes, fine tuning is preferred because you do only one time training and you're done. For evolving knowledge that changes frequently, RAG excels because you don't need to retrain, you just re embed the updated documents. For hybrid needs where you have some stable foundational knowledge and some current information, you should fine tune base capabilities and add RAG for the current data. We'll see examples of this in hybrid approaches in just a bit. The third is quality requirements. For high quality thresholds where you need the absolute best performance, fine tuning typically achieves the best task specific performance because the model is optimized end to end for your specific use case. For good enough quality where the perfection is not required, base model with optimization is often sufficient and much more faster to deploy. When explainability is needed and you must be able to cite the sources, RAG provides much more natural citation framework. The fourth is data requirements. For simple classification tasks, you need 500 to 200,000 examples. For complex reasoning tasks, you need roughly 10,000 to 50,000 samples. For domain specific language, you need roughly 20,000 plus examples. If you don't have sufficient training data, fine tuning is unfortunately not the option, regardless of the other factors. So, the key here is to evaluate all these four factors together, not in isolation. You might have a high query volume pointing towards fine tuning, but if your knowledge base changes daily, RAG might still be the better choice. Now, in practice, many production systems don't just use one approach. They use hybrid architectures that combine multiple strategies, so let's explore that. So, in my experience working with production systems, the most sophisticated architectures often combine multiple approaches rather than just focusing on one and just sticking to it. So, let's cover some common patterns. So, the first pattern is fine tune base plus RAG. So, you fine tune a model for domain language understanding, teaching it medical terminology, legal language, or your company's internal jargon. Then you add RAG on top for current facts and data that change pretty frequently. This gives you best of the both worlds, efficient domain understanding from fine tuning and up-to-date information from RAG. The second pattern is tiered models plus caching. So you route by complexity to different model sizes and you cache frequent queries at all tiers. Simple queries hit the cache or go to small models, complex queries go to large models. This compounds your cost savings because you're both routing efficiently and avoiding the redundant computation. The third pattern is RAG plus aggressive optimization. So you use retrieval for context, but you apply token optimization and semantic caching aggressively. You might be doing retrieval, but you're minimizing the token count you send to the LLM and caching the semantically similar queries. Now let's cover a concrete example. For example, let's say you're designing a technical documentation system, and over there you can actually combine multiple of these approaches. You can essentially use the fine-tuned model for code understanding because that foundational knowledge is stable. You can use RAG for API documentation retrieval because that changes with every product release. And RAG implements the semantic caching for common questions because developers ask similar questions repeatedly. And then it uses the tier routing for query complexity. So for simple, how do I import this library questions can go to small models, while complex debugging questions can go to large models. The result was can be essentially in this you can optimize by 35% lower cost than a pure RAG approach while maintaining the same quality. So now a word of caution on implementation considerations. Hybrid approaches increase architectural complexity pretty significantly. You need to ensure that you have engineering capacity for building, monitoring, and maintaining multiple subsystems. So my recommendation is to start simple and add complexity as volume justifies the investment. Don't just start off with building the most sophisticated architecture on day one. Build what you need right now and then you evolve as you grow. With many of these architectures, you need strong cost management and governance. So let's talk about that next. So as part of cost management, which is super important because without proper controls and monitoring, costs can spiral out of control pretty quickly, especially with GenAI applications. For essential controls, the first is per team quotas. You should limit API usage by team or project to prevent the runaway costs. If one team's experiment goes pretty haywire and start making millions of API calls, it shouldn't take down your entire budget. Second is rate limiting. You should set maximum requests per hour and per day at both the application level and the user level. This protects you from both bugs and abuse. The third is the budget alerts, which is to essentially you should configure notifications at let's say 50%, 75%, and 90% of your monthly budget thresholds so that you have time to react before you hit your limit. For key monitoring metrics, the first is cost per query. Track the average cost including all components, embedding, retrieval, and inference. This is fundamental unit economics. The second is token consumption trends. Identify queries with unusually high token usage because these are opportunities for optimization. If you're seeing 10,000 tokens prompt regularly, something's probably wrong with your prompt engineering. Now, third is the cache hit rates. You should definitely monitor the effectiveness of your caching strategies over time. If your cache hit rate drops from 40% to 10%, maybe your query patterns have changed and you need to adjust. Fourth is cost by feature. Attribute spending to specific product capabilities so you can essentially make ROI decisions about which features to keep, expand, or sunset. For reserved capacity strategy, here's where you can get significant discounts. 1 year or 3 year GPU commitments for self hosted models typically offer 30 to 50% discounts for all major cloud providers like Google, AWS, and Azure. The key is to commit it to your baseline usage, which should be roughly 60 to 70% of your typical spend, and handle peaks with on demand capacity. This balances cost savings with flexibility. You should analyze 3 to 6 months of your usage data before making any long term commitments to ensure that you understand your baseline load. So, for example, a company, let's say with $20,000 per month LLM API spend comes to $12,000 per month, which is roughly 60% of their typical usage at a 20% discount. This saves them $2,400 per month or about $29,000 per year. The remaining $8,000 of variable usage is handled by on demand for flexibility when they do have spikes. The strategic principle here is that you cannot manage what you don't measure. Implement comprehensive monitoring from day one, even if your costs are small, so you should have the data to make the decisions as you scale. So now let's wrap up with the key takeaways you should remember from this discussion. So now let's essentially synthesize everything what we have covered into actionable takeaways you can use when making architecture decisions. First is architecture trade-offs. Fine-tuning has high upfront cost and low per query cost, making it best for high cumulative volume situations where you will execute millions of queries over the model's lifetime. RAG has zero upfront cost and moderate per query cost, making it ideal for evolving knowledge bases that change frequently. Base models offer the faster deployment with moderate cost, making them good for experimentation and validation before committing to more complex architectures. Second is that the optimization is actually universal. Caching, token optimization, and routing apply to any architecture you should choose. These techniques are complementary and they are not alternatives to your architecture decisions. Production systems should implement multiple optimization layers. Don't just optimize tokens, but you should also implement caching and also do model routing so that the savings actually compound. The third is the decision criteria. You should focus on total cumulative query volume, not just your monthly rate. A system doing 100K queries per month today might be doing 1 million per month in a year, which will completely change the economics. Consider knowledge update frequency and quality requirements together with volume, and also perform 12 to 24 month TCO analysis for informed decisions, so not just depending on the monthly cost comparisons. The upfront costs in fine-tuning only make sense when viewed from a longer time frame. The fourth is continuous improvement. Implement comprehensive monitoring and cost attribution from day one so that you should also be doing review the metrics weekly and identify any optimization opportunities that may arise. You should iterate on the improvements and measure the impacts systematically. For example, what works at 10,000 queries per month might not work at 1 million queries per month, so you need to constantly reevaluate. The fundamental insight is that there is no one size fits all answer. The right architecture depends on your specific workload characteristics, and those characteristics may change over time as you scale. Start with a simple architecture that meets your needs, monitor carefully, and evolve as your requirements and scale change.